Alrighty. We actually haven't had lecture in a while, so one thing that I wanted to cover before we start is the mask mandate. So, as far as I understand, it's been lifted by the university, and I don't plan on, imposing any additional guidelines beyond what the university has specified. I would only incorporate one suggestion, which is that, come to lecture however you feel comfortable, but do think about also the comfort of people around you. So, if anyone, needs to figure out like how to, organize themselves in order to make everyone feel comfortable coming to lecture, do that. Try to do that amongst yourselves. If that doesn't work, feel free to come talk to me. I would also suggest that if you come ask me questions after lecture, that you do wear a mask. I'll still be wearing one, but again, it's everybody's choice. And I, tend to follow the university on these things, so I won't be imposing anything else beyond that. I've also been told that, so that was one thing. The other thing I've been told is that there's a lot of announcements for this week, more than can fit into whatever I say at the beginning of class. So just do check Piazza later. They should be posted. Okay, but we're moving on, and we're going back to content. So talking about something called nearest neighbor today. Okay, so what is today's lecture about? Well, so far in this class, what we've focused on almost exclusively, right, are these methods for linear regression and classification. So you learned about all of these different linear models, right? Linear least squares, least absolute deviations, ridge, lasso on the regression side, right? Logistic regression, perceptron, SVM, linear discriminant analysis on the classification side. All of these things are linear, right? We've pretty much learned purely linear things. But then what we did, at least in the last couple of weeks, right, is to combine these ideas, these models, with featureization, in particular kernelization and the kernel trick, right, in order to get nonlinear models, right? We take our features, we pass them through some featureization, like, for example, some particular kernel, to get nonlinear features on top of those, and then use a linear model on top of that, right? And then the model, at least with respect to the original features, is a nonlinear model at that point. This is, by the way, an idea that's not restricted to kernelization, right? In fact, when we talk about neural networks for like the last 3 weeks of this class, that's kind of one of my favorite ways to understand neural networks. It's basically a linear model on top of these learned nonlinear features, rather than features that we specify, for example, via kernelization. But we'll get there when we get there, right? Instead, what we're going to do this week is we're going to first study two models that are essentially, by definition, by construction, nonlinear. Okay, just based on the way that we define them, there's no, featureization tricks or anything like that we need to do in order to make them nonlinear. They're just straight up nonlinear just from the start. And in particular, today what we're going to talk about is a model called nearest neighbor, the nearest neighbor model. And then on Wednesday and Friday, we're going to talk about decision trees. What you might be able to see, especially from the last like 4 or 5 slides in this lecture, is that nonlinear models are oftentimes either harder to learn, or they're harder to use, or they're harder to analyze. Okay, when things are nice and linear, we just get a lot of things essentially for free. How to analyze these things and how to learn them and all this other kind of stuff. But once we turn things nonlinear, things become more complicated all of a sudden, and we have to make all of these different trade-offs and things like that. However, nevertheless, it is very useful to know about these nonlinear models because nonlinearity buys us a lot. And so these models can oftentimes work better and are oftentimes, quite popular in practice. Especially, when we talk about decision trees on Wednesday, we'll probably talk about random forests on Friday, which is kind of an extension of the decision trees idea. At this point in time, in 2022, random forests are still extremely popular, maybe only second to like deep neural networks and deep learning in general. So knowing about random forests is still a really, really good idea. And there are many places where nearest neighbor would also be a good idea. So it is good to know about these things in general. But let's start with a little bit of sort of context about why we might study these nonlinear models. Okay, so we've already learned how to use featureizations, right? For example, the kernel trick. in order to make in order to make linear models nonlinear. We already talked about that, right? So then why would it be the case that we still need to learn about models that are inherently nonlinear? What is the point of that? Well, if you look closely at some of this like kernelization, kernel trick stuff that we've done so far, you might start to notice some of the flaws behind the idea. I mean, it's a beautiful mathematical idea, the kernel trick, right? But it's not without its flaws. The kernel trick is a great tool, but it really only allows for some featureizations, right? So it allows for us to use these featureizations phi that can be written down as some simpler like inner product between these different featureizations of data points, right? That's what we're kind of limited to when we talk about the kernel trick. And also, we have to define models that are compatible with kernelization, right? We have to define these models that can be written entirely in the form of these inner products between data points, right? And that's true for both training and prediction. We have to always be able to do this. And it's not always going to be the case that everything's kernelizable. A lot of models are, as we've seen. But then sometimes we have to play all these different math tricks, like look at the dual and all this other kind of stuff, which just, introduces additional trade-offs between number of data points versus your feature dimension and all this other kind of stuff that might not be very desirable, right? So the kernel trick is great. There's a lot of reasons why we would want to use it, but it's not complete, so to speak. And so the models that we're going to learn this week, as well as later in the course when we talk about deep neural networks, for example, they really further push the boundaries of what types of problems we can tackle. So it's really good to have this like full arsenal, this entire toolkit of different models at our disposal, right? So that when you encounter a new problem, you have the whole set of models available to you, and you can reason through what might be the best model for your particular problem. That's the goal of what we're doing, before, this week, and beyond. Okay, so let's talk about nearest neighbor. Nearest neighbor is simple enough, actually, to sort of summarize in 2 slides, basically. It really is the simplest model to explain. Some classes actually start with nearest neighbor because it's so simple. We didn't do that in this class. There's sort of a different progression that we follow. Nevertheless, it'll only take about 2 slides. So nearest neighbor does nothing at training time. Okay, literally do nothing at training time. It's the only O of 0 learning algorithm. So if you're not familiar with this like big O notation about asymptotic analysis on algorithms, don't worry about it too much. All this is basically saying is that it's really the only learning algorithm that we can imagine that specifies basically no training procedure whatsoever. The only thing that you have to do is store all of your training data. Okay, so we're still assuming, of course, right, that we're giving some training set, xi, yi for I equals 1 through n. So we're given n of these training points. And all we're going to do at training time is just store them. Well, we assume that we already had them, right? So we're just going to keep them. That's basically all we're doing, right? So at least in the most naive version of nearest neighbor, there's nothing else that we have to do. Just store all of our training data. Test time is a little bit more involved, but still explaining what we do at test time is equally simple. Okay, the actual procedures, as we'll see in a second, are getting a little bit more complicated, but basically all we have to do at test time, if we're given a new point, let's call it x prime, all we have to do in nearest neighbor is compute the closest point xi from the training data, and then whatever label or target that training point had, we just predict that as well. And this procedure applies for both classification and regression, right? So if yi is some discrete label, right, then we just return that label as our prediction. And if yi is some real value target, we again just return that value as our prediction. And this is literally all nearest neighbor is doing. Okay, so at training time, do nothing. Just make sure that you keep all your data around. And then at test time, when we're given a new point, just make a prediction according to whatever training point was closest to this point that we're trying to make a prediction on. By the way, as an aside, nearest neighbor is an example of a class of methods that we would call non-parametric. Okay, so non-parametric can mean a lot of different things. I didn't put this in the slides because it's not crucial that you know this, but I do think it's kind of interesting. Non-parametric can mean a lot of different things, but oftentimes kind of the way that we think about non-parametric methods in machine learning is that sort of the number of parameters that you have grows with the size of your training data. Okay, that's the way that a lot of people like to think about these things. So a parametric method, right, is something that defines a fixed parameter size, right? Like a weight vector or something like that. So a lot of like the linear methods that we learned before, at least in their original forms, they're parametric methods, right? Whereas a non-parametric method basically says, well, maybe I do have parameters, right? Or something that I can treat like parameters, but maybe they're learned, maybe they're not. But these parameters, right, they have a variable size based on how much training data that I have. And nearest neighbor kind of fits very neatly into that, right? Because we can almost think of the parameters as like our data, right? We don't learn them, but those are the things that we need in order to make a prediction, right? And the data obviously grows as a function of the data. That's kind of just trivial. So can anyone think of anything else that we've learned in this class that's non-parametric? It might not be immediately obvious, but think back to situations that we've had where maybe the learning problem that we're trying to solve is dependent on the data size. Yes. So SVMs, be more specific. That is absolutely on the right track. So yeah, so that's absolutely on the right track, right? So basically, if we have, for example, the dual version of the SVM, right, where the parameters that we're trying to learn is this alpha vector, right? This alpha vector is an n-dimensional vector, right? What is n? N is the number of data points, which means that as we have more and more data, the size of our parameters actually grows, right? In more generality, most, if not all, of these kernelized versions of these algorithms are non-parametric, right? Or that at least they can be understood as non-parametric methods, because a lot of the times what we're doing is analogous to trying to learn something like that alpha vector, right? Something that is going to be variable size depending on how much data that we have. And SVMs are a great example of that. They learn these alphas, and then that's how we determine the support vectors from our data. But in the primal version of the SVM, right, where we're just learning a weight vector W, right, that is a parametric method because that W is a fixed length regardless of how much data that we have. That W depends on the dimensionality of the data. Okay, yes? That's a great question, right? So ridge regression, even kernelized, is parametric, right? No, actually it's not, right? Because ridge regression, so ridge regression is a little bit strange, right? Because in ridge regression, when we kernelize it, right, we actually we're not actually necessarily able to write down W star, right? Because W star, unless we're making a prediction, right, just W star itself depends on like these phi of x's, which we might not be able to write down, right? It's only when we make a prediction that we're able to actually, write down W star transpose x, right? Because that turns into like evaluations of my kernel function, right? So in that sense, it's kind of hard to say, like, is it parametric, is it non-parametric? Like, we're not writing anything down until we actually make a prediction. In that sense, I guess it kind of is non-parametric, right? Because what we would have to do in order to make a prediction is keep around all the data. And if we, treat that in the same way that we treat nearest neighbors, then we're getting to the same conclusion that, the amount of stuff that we're learning, or at least have to store, grows as a function of the data. Okay, so now back to nearest neighbors. So nearest neighbors is non-parametric, and, at least on one slide, the naive nearest neighbor algorithm, or the nearest neighbor model, is extremely simple, right? Do nothing at training time, just store your data, and then at test time, compute the closest point and return that corresponding prediction. There's a very important modification to this general idea, which is very simple at the same time. And it fixes this following problem. So the nearest neighbor model that I've just described, it can be susceptible to things like outliers and noise, right? So if you get unlucky and it just so happens to be the fact that the closest point to you is some kind of weird outlier, or it's a point with like a noisy label, right? Like that point or even it was mislabeled or something like that, right? These things can all mess up your prediction when we're only looking at a single nearest neighbor to make our prediction. So one way to essentially quote unquote smooth out this model, and I put these in quotes when I say things that are not necessarily like technically rigorous, but you sort of get the intuition behind it, right? One way to smooth out this model is to instead consider the k closest training points to a new point x prime for some k greater than or equal to 1. And for certain reasons, this k is often chosen to be some small odd number, like 3, 5, 7, 15, something like that, right? And then doing this essentially allows your model to be a little bit more robust to the different types of outliers or noise that you might see in your training data. Why do we use an odd number most of the time? It's because if you're doing classification at least, what we're usually going to do is predict according to a majority vote amongst the training points. So if you use 3 nearest neighbors, right, and 2 of them say the label is +1 and 1 of them says the label is -1, then the 2 outvoted the 1, right? So now you're going to predict +1 as the label for this test point, right? And so that's why it's useful to have an odd number, at least for binary classification, right? Because then you'll always have, you'll never have the situation where you need to figure out some kind of tiebreaker. For regression, it doesn't matter as much because basically all we do there, when our y's are real valued targets, right, is just average all the targets together in order to make our prediction. So nothing particularly more complex, right? The training time thing is all the same, right? All we do is store our training data. Now the test time procedure is a little bit more complicated, but it's still fairly simple and intuitive, right? Take a majority vote or average all of the targets together. And the reason that this is useful is because if we have outliers, typically we can think of these outliers being quote unquote outcompeted by other points. So if one outlier was really strange, gave you some really weird y, right? Well, we tend to sort of either average that out or it gets voted out based on all the other nearest neighbors. Whereas if you have, sort of like noisy labels or, noisy points, these also tend to be averaged out by the other neighbors that you have. So that's the basic idea behind k nearest neighbor. It's not that much more complicated, but it is, generally speaking, a much better idea than one nearest neighbor. And we can actually see this pretty clearly based on, if you remember, some of the plots that I showed you in lecture 1. Okay, so in lecture 1, I showed you this, this toy data set with like blue points and orange points. And then we drew different types of decision boundaries between the blue and the orange, right? And one of the ones that we drew was this one nearest neighbor point. This looks a little stratified for some reason, not sure why. Anyway, so here, right, like I said, we have these blue points and we have these orange points. And if we have a one nearest neighbor classifier, we get something that looks pretty wonky, right? But you can also understand exactly what it is that it's doing, right? For any point that we would want to do classification on, right? Like any, x1, x2 in this 2-dimensional data set, right? We can figure out which point is closest to it and then sort of split up our data or split up our, domain into these regions, right? Where we would predict blue versus predicting orange. And we can start to see some of these like weird phenomenon that are popping up, right? Like we have, these like little pockets, for example, where it seems like, well, maybe that orange is not actually representative of what the majority in that region would be, but when we're only considering one neighbor, right? We run into these weird regimes where we're a little bit more susceptible to the noise in these regions. Same goes for the blue over here, right? This is not sort of the dominant data in that regime, but nevertheless, it's kind of the closest point that you have, and so you might be doing some weird stuff if you only use one nearest neighbor and getting these like very rough decision boundaries that might not correspond to the one that generalizes the best, right? As compared to if you scale up to something like 15 nearest neighbors, right? So what that means is that for any point x1, x2 that I have, right, what I do is I try to figure out what are the 15 closest points to me, right? And this is a classification task, right? It's binary classification in particular. And so what we're going to do is we're going to look at the labels of those 15 closest points and then take a majority vote to figure out, should I predict blue or should I predict orange, right? And here we can see that, essentially what this 15 nearest neighbor does, at least pictorially, right, is it really smooths out, the rough edges, the jagged lines, the, places where we're susceptible to outliers and noise and things like that, compared to this one nearest neighbor decision boundary. And so that's kind of the thing that we're doing here. That's kind of nice about, scaling up K, essentially. We can see here, right, that like we were saying before, this nearest, well, both of these decision boundaries, but let's focus on this one because this one looks nicer, right? These nearest neighbor boundaries are inherently nonlinear, right? I didn't have to define anything like a parameter vector or anything like that, right? In order to say like, well, my decision boundary is parameterized by this theta, because when I do that, right, there are certain limitations that I'm placing on the problem, right? I'm saying that I have to figure out what a good representation for theta is, and a lot of the times for simplicity, we just said, well, theta is a weight vector and it's going to be a linear boundary, right? We don't have to do that here, right? We never define any kind of theta or anything like that. We just defined our decision boundary according to the data. And doing so allows us to learn, some very interesting kind of like flexible decision boundaries that might better represent the data as long as we have enough of it, right? So the conventional wisdom behind nearest neighbor classifiers is that they work really well when you're trying to learn complex decision boundaries in low dimensional spaces, okay? I will explain to you a little bit later why we have to make this caveat that we're looking at low dimensional spaces, but in general, when we have that, like if, D, the dimensionality is something like 20 or below, say something like that, we have, sufficient data, and we believe that, our decision boundary is going to be something more complicated than like, linear or some kind of kernel features that we can define, then this nearest neighbor classifier oftentimes works really well in terms of sort of, accurately representing that decision boundary that we want to find. And we can see here, from this simple example at least, that it kind of looks like the 15 nearest neighbor is doing something pretty reasonable for, something that's a little bit more complex than linear is how we want to represent this. In fact, we actually can analyze this, nearest neighbor approach for this particular problem in a little bit more detail, because actually this particular problem doesn't correspond to like real data that we collected for some problem. This particular problem corresponds to data that we generated according to some distributions that we defined. Okay, in particular, each of these orange and blue were kind of defined according to some like mixture of Gaussian distributions and things like that. And so we actually know what the sort of quote-unquote optimal classifier is, the optimal decision rule is for this particular problem, and it actually looks something like this, okay? How do we figure this out? Well, it's because we know the underlying distributions, and so we can compute what we call the Bayes optimal classifier. We've already, talked about this a little bit, right? Where basically the Bayes optimal classifier basically just, minimizes the probability of making an error based on, the classifications that we're making, right? There is noise in this problem, right? Like each one of these orange and blue points, they come from distributions that happen to overlap, right? So it is never going to be the case that we can be perfect, right? We're never going to drive that error to zero, right? But this essentially is a decision boundary that we can compute for this problem because we know those distributions, right? We can compute that, and this is the one that minimizes that probability of making an error. And we can see actually, that this decision boundary for this problem, it's, not dissimilar kind of to like this decision boundary that we learned here for this nearest neighbor. It would have been nice if we had like, figured out that like, we also need something like that, but, we didn't have necessarily sufficient data to figure that out. And maybe if we had more data, we would have. But nevertheless, this 15 nearest neighbor seemed like it does a pretty good job at, approximating this, this best decision boundary that we hope that we can learn. Yes? I'm sorry, could you repeat that one more time? Right. So the reason that we call this 15 nearest neighbors, right, is because if I have like some test point, okay, that I'm trying to classify, so this is like a new x that I'm given, right? When I'm trying to make that classification, what I'm doing is I'm trying to figure out what are like, the 15 closest points. I don't know what I'm drawing anymore. The 15 closest points in the training set to that point, right? And then we just look at the labels of those 15 points and we figure out, are they majority blue or are they majority orange? And then that's what we predict, either blue or orange accordingly. How did I choose 15? Oh, I didn't choose 15. Whoever wrote this book chose 15. But a small odd integer is usually a pretty good choice. 15 is actually fairly common. This is a hyperparameter, by the way. K is a hyperparameter that you'll have to choose by yourself, or maybe use validation or cross-validation in order to choose, right? But these small odd integers are very common choices. If all we're doing is predicting labels, how is that decision boundary drawn? So, okay, I think I understand what the question means. And basically, this decision boundary is sort of like not what you're actually computing explicitly in nearest neighbor, right? You're not really computing anything explicitly except for like a single prediction when you get a point, right? The way that this was, the way that this was visualized was essentially by gridding this entire space and then just going through and then figuring out for every single point on this grid what I predict orange or what I predict blue, and this is only for visualization purposes to kind of draw that decision boundary. Okay. So 15 nearest neighbors seems to have done a fairly good job at learning a good classifier, at least compared to the best one that we could possibly learn, right, this Bayes optimal classifier. We didn't quite get there because it kind of seems like maybe we didn't quite get enough data to understand that there's something different in this regime that we have to do, right? But maybe if we had seen more data from the entire space, then we could have gotten to the sort of gold standard that we're reaching for, right? And actually, we can prove this to be the case. Okay, so I'm actually not going to prove it because the proofs get, quite mathematically rigorous, and it's not fun to do that, especially after your midterm last week. But we're also not going to worry about the proofs in this class. I'm just going to show you the results. If you're really interested, you can go look them up, right? But it's going to be considered out of scope to actually dive into the mathematically rigorous details of the proofs. But the results, at least when we're presenting them informally, kind of look like this. If I have a nearest neighbor classifier, so here when I'm saying nearest neighbor, right, and anywhere where I say nearest neighbor and I don't say k nearest neighbor, right, I'm saying k equals 1, okay? So when I just say nearest neighbor classifier, I mean you're only looking at the single nearest neighbor to your test point, okay? For a nearest neighbor classifier, as your n goes to infinity, okay, so as you essentially have, all the training data that you could imagine, right, the error rate for a new test point that you get converges to at most twice the error rate of this Bayes optimal classifier. Okay, so you'll essentially be no more than twice as bad as your Bayes optimal classifier, which is actually pretty good a lot of the times, right? I mean, like the Bayes optimal classifier for problems that have relatively like low noise, right? Like where all your different classes are well separated and they don't overlap very much. You can get Bayes optimal classification rates of like close to 100% basically, right? And so your error rates will be close to 0%. Twice of something close to 0 is still very small. So you can basically say that this nearest neighbor classifier, as it's getting enough data, is doing really, really well. Okay. Why is it twice? Well, again, this is we have to get into the math of it, but the intuition behind why it's twice is because there's essentially what we consider to be two independent ways that we can mess up. Okay. The one way that we can mess up is that our new test point is sort of like in the minority class of what we didn't predict, or the nearest neighbor that we're looking at is in the minority class of what we didn't predict. Okay, so because we have these two independent sources of error, the new test point and the nearest neighbor that we're comparing to, what we get is essentially twice the error rate of the Bayes optimal classifier. However, we can do better than this, right? We already said that nearest neighbor classification is not necessarily a great idea by itself. So we can look at k nearest neighbors, right? And here, the proof gets even more complicated, and even stating the result is a little complicated, but basically, it's as follows. Again, as the amount of data that you have goes to infinity, right? So you have, essentially what we're saying is we have sufficient training data, right, for the problem that we're interested in. And as the number of neighbors that you consider k goes to infinity, okay, but we can't have the number of neighbors growing larger or even the same as the amount of data that you have, right? Because that wouldn't make sense. You only want to consider a small number of neighbors for your whole data set, right? So we're going to also want k over n, that ratio, to go to 0, okay? So we have way more data than the number of neighbors that we're considering, right? As those things hold, the error rate converges to literally the Bayes error rate, okay? So no 2 times nonsense, right? We're literally getting the optimal classifier that we could possibly hope for this problem, okay? So that is, in a sense, a very interesting result, actually. It basically says that k nearest neighbor is the best that we can do in this sort of infeasible asymptotic regime, where we get as much data as needed in order to learn the particular function, and we do something a little bit smarter than just one nearest neighbor. We do this k nearest neighbor instead. So when I took this class back in the Stone Age, right, we had a professor that was, he was like very much like really into nearest neighbor, okay? And like the meme was that like if you went and talked to him about a problem, he would always just say like, oh, have you tried nearest neighbor? And it was basically for these reasons, right? That nearest neighbor oftentimes works really, really well as long as you have sufficient data. And so, of course, because he was teaching the class, there was this one question that we had on our final. I'm going to read it to you. It says, it's a true-false question, and it says, if we had infinite data and infinitely fast computers, k-nearest neighbors would be the only algorithm that we would study in CS189. I knew that the answer was true because I knew that it was this professor that wrote it. I don't necessarily know if I agree with the sentiment. I mean, these other models are, still interesting and stuff, right? But you can sort of see where this is coming from, right? Like infinite data and infinitely fast computation. I mean, once you have like infinitely fast computation, would you even study machine learning to begin with? Like, I don't even know if that's if this even kind of makes sense, right? But if CS189 still existed and we had these things, it would make a whole lot of sense to basically focus all your time on k nearest neighbors because it's literally the optimal classifier, right? Like that kind of makes sense in that regime. Yes. Who was the professor? Alyosha Efros. A little more focused on deep learning these days, but again, this was way back when. So, deep learning wasn't as big of a thing back then. So that's kind of cool. So we've kind of established actually that, there are pretty good reasons to study nearest neighbor classifiers, at least, in theory, and also in practice, they're very simple. And like what I said before, right? They're quite good at learning these complex decision boundaries in these low-dimensional spaces, right? So when you have a type of problem that kind of fits that mold, you think that the decision boundary is going to be something more complicated, but you only have like 20 dimensions or something like that. Nearest neighbor is oftentimes a very good algorithm to kind of throw out that problem, at least something to try. But it comes with its challenges, right? If it didn't, then again, we would only study this, but it definitely comes with its challenges. So these models seem great. They're really simple, and at least sort of, speaking, they're theoretically optimal, right? Sort of because you have to have infinite data, which, and it's not really saying that much about the finite data regime. Nevertheless, it enjoys some of these guarantees, which seem kind of nice. So what is the catch? Okay, what are some of these potential issues that we might run into with nearest neighbor models? I have 4 things that I came up with, and I tried to list them in order of how likely I think it is for someone to be able to give me that particular reason. So now I will solicit suggestions about what might be not so great about nearest neighbor models. Yes? We have to store all the training data, right? I'm so good at this. So that might be impractical or infeasible, right? in particular, imagine that you have, some kind of deployment scenario, right, where you have like a really large computer or supercomputing server that you can use to train your model, right? So there you can store all your data, right? But what you want to do is like deploy your model, right, to like, everybody's cell phone or something like that. Well, everybody's cell phone, there's no way they're going to be able to store all that training data, right? So that kind of defeats the purpose of this approach, right? So in a lot of practical scenarios, you can imagine that having to store all this training data might be super impractical or super infeasible, okay? So that is definitely a good one. There's no great answer to this problem. If this problem, resonates with your problem, then you probably don't want to use nearest neighbor. That's kind of the extent of it. There are, however, some problems that we're going to list here that also, are issues, but they might be solvable still with nearest neighbor classification. Okay, or nearest neighbor regression. Okay, what else can we think of? Yes? Are y'all just looking at my slides? I mean, yeah, absolutely. So apparently, right, or at least it seems this way, we have to loop through the whole training data set to make a prediction, right? So say that you've gotten past the first issue, you're able to store all your training data, okay? But if your training data is really large, then it's really impractical to make a new prediction on your data point, on your test point, right? You have to, apparently, it seems like we have to loop through the entire training set, compute a distance, right, between our new point to all the training points, maybe store like, the closest 15 or something like that, right, in order to make any prediction at all. And it seems like doing this for every single prediction that we want to make is probably a really bad idea. We will talk about ways that we can sort of, kind of get around this problem, but nonetheless, it is still a particular problem. Okay, the last two, I think, are a little bit trickier, but can anyone else think of any other problems that we might have with nearest neighbor? Yes? Could be hard to find the right k value. That's not one that I listed, but that's true, right? We have hyperparameters that we need to tune, right? It's not immediately clear to me if hyperparameters are harder to tune in this scenario compared to other models, but nevertheless, we do have things that we're going to need like validation or maybe cross-validation and things like that in order to figure out. Yeah. Fantastic. Yeah, so that's actually the last bullet point that I listed. So yes, we will definitely get there. Yes. Super interesting. Okay, so we have things like class imbalance or an asymmetric loss function, right? And nothing that I described so far is actually going to be able to take care of that. We might be able to figure out ways to fix that, right? We take like a weighted vote of like the different classes or something like that. Nevertheless, it is another problem that we would have to deal with. Absolutely. Yes. Lack of data. Absolutely. So this is, in a sense, related to this third point that I have, also related to what we had earlier, right, about essentially there's a problem that we have called the curse of dimensionality, okay? The curse of dimensionality actually is not specific to nearest neighbor classifiers, but it is very true that nearest neighbor classifiers suffer significantly from this problem, where essentially the problem that we have is that we need exponentially more data in high dimensions because basically all data points in high dimensions are far away from each other, okay? So I'm not going to explain this mathematically. All I'm going to say to you is that whatever intuition that you have about high dimensional spaces and how you might visualize them, they're all wrong, okay? Like we have no capability as humans to understand high dimensional spaces, and you can look up all these really interesting facts about high dimensional spaces that would probably blow your mind because it just corresponds nothing to the intuition that we have, okay? So in particular, the problem that we have with high dimensional spaces and nearest neighbor is that we don't really have any neighbors that are particularly close to each other, okay? It's very easy for all of your data points to be really far away, and therefore nearest neighbor kind of starts to break down because unless you have exponential amounts of data, right? Where basically we're saying like if you have, D dimensions, you need like, something like e to the d data points in order to cover that well, right? Then you start to get really, really, infeasible data needs very quickly as your data dimensionality grows. So that's why we said specifically complex decision boundaries in relatively low dimensional spaces is kind of where nearest neighbor shines. As you get into these high dimensional spaces, you start to get these, really weird, artifacts and things that, we don't expect to work. And this is kind of the underlying issue behind that, the curse of dimensionality. So I should say that curse of dimensionality is a more general term, right, that basically corresponds to any kind of model trying to learn something in a high dimensional space. Nevertheless, it is very true that nearest neighbor is one of the most prominent examples of a model that suffers from this problem. And the last thing is basically what we already said, right? What somebody already said, which is, how should we even define distance to begin with, right? So I said, like, find your nearest neighbor, find the point that's closest to you. What does close mean, right? How are we defining these different distances? And our simple distances, for example, we can think of like Euclidean distances or things like that, right? Are those always a good idea, or might those start to break down depending on what problem we're dealing with? So those are the things, at least that I listed, that we're going to have to try to figure out, or hope that it's not the case, right, in order to make nearest neighbor models actually work. Yes? Interesting. So when we go back and talk about kernels, right, nearest neighbor actually can be kernelized. We won't see that in this class, but it's another thing that you could imagine popping up somewhere, right? And when we think about something like the RBF kernel, right, essentially, implicitly at least, what it's defining is some kind of like Euclidean distance between different points, right? The issue, right, is that when we get into this last bullet point here, we're not actually particularly confident whether or not Euclidean distance is really even a good idea to begin with for the types of problems that we might want to deal with, right? And we're going to see a very concrete example of why that might not be the case in a few slides. Yes? Interesting question. Are you asking about like maybe like what's a rule of thumb for like D? Yeah, interesting. So as far as rule of thumbs go, I would have to imagine that you probably want your data to be in no more than like probably like a 20 to 40 dimensional space for nearest neighbor to work well. I mean, you could go up to 100 as long as your data has good structure, right? But like beyond that, you're really starting to push the boundaries. And that depends a lot on like how much data that you have as well, right? So if you can collect a large data set, right, then maybe something like up to 100 dimensions could still work decently well. Again, depending on the structure of your data, depends on how you do the dimensionality reduction if you do it, right? And then it also factors into, in complex ways, other things like how do you define your distance and all these other kind of questions, right? If you can define a pretty smart distance function, right, then maybe you can scale that up even more into like 1,000 dimensions or something like that, as long as the distances kind of make sense in that 1,000-dimensional space, right? So a lot of these things get to be fairly complex, like interrelated concepts. But general rule of thumb is that if you don't know those things a priori, then scaling past like 20 to 40 is going to be pretty difficult without a very large data set. Yeah. Oh, is it mandatory to use the same distance for each feature? That's a really interesting question. The answer in general is no. So we can consider things like, for example, well, I wasn't going to talk about it in this lecture, but just very briefly, there's a concept called just as one example, right? There's this concept called Mahalanobis distance, which basically says, take your data and like fit a Gaussian to it, and then use like that Gaussian corrected sort of like, density as like your distance metric, right? And so we think about doing this, basically what that's doing is kind of measuring distance differently along all of these different directions of variance, right? So you could have a point that's closer in Euclidean distance, but if the variance is much smaller in that particular axis, then it's going to be treated differently than this other axis, which might have a larger variance, right? So we can define all these different things that sort of are kind of maybe more dependent on the data set, which might, do things implicitly like weight features differently and things like that, that would measure distance in a more data set specific way. Yeah. Is it common to use different distance metrics? That's a good question. I mean, I guess probably the thing that most people do is like try to pre-process their data so they don't have to. But it is sort of like one of the more advanced things that you could try to make these models work better. Yeah. Okay, I have a couple more slides, so let's finish through this, and then we can take more questions afterwards in office hours. Let's talk about this first problem, where we have to essentially loop through the entire training set in order to find our nearest neighbors. This is actually, in general, not a problem that you can get around, but there are certain ways that you might be able to sort of get around it that are good enough, so to speak. So if you naively search through your entire training set and you compute a distance for each point, again, back to this asymptotic big O notation, you can ignore it if you want to ignore that big O. The thing that's important is inside those parentheses is d times n, right? So n, because we have to do this for every single training point, and d, because usually computing a distance for two d-dimensional vectors is an O of d operation, okay? And so doing this is going to be really bad if you have, either like very high dimensional data, which maybe you don't because you wouldn't be using nearest neighbor in the first place, or if you have a ton of training data, which could definitely be a problem. There are some cases which we consider sort of like nice problems where your data has a nice distribution, where you can essentially think of smarter ways of storing the data at training time. Okay, so at training time, you get all this data, and then you put it into some particular data structure, for example, something called a KD tree, which we're not going to get into in this class, but it is sort of like, a term that you can look up on your own if you find it interesting, which can result in sort of on average logarithmic runtime in terms of the number of data points that you have to search through, right? And the kind of reason for this is you're storing your data in a binary tree, so at every point you can say like, let's split my space in half, right? And then only look at half of that space, and then we do that, some number of times in order to figure out what the nearest neighbor might be. But this is sort of an imperfect regime, right? Because we might have to still look at the other branch, so to speak, in my KD tree if I'm trying to check for outliers and things like this. So we're going to get more into detail on that in homeworks, but it is a good thing to know that, on average, we can sort of improve the runtime of how many data points we actually need to look at. Arguably, I think what's actually more important than these things is that in many cases, it's actually pretty good and good enough to just use an approximate nearest neighbor, okay? So not have to make sure that you guarantee that you find the closest neighbor or the 15 closest neighbors, but sort of like 15 neighbors that are quote unquote like close enough, okay? They're pretty close. Oftentimes, this is actually a good enough procedure for, finding a prediction that's fairly decent. And so these types of approximate nearest neighbor search methods are really quite popular because they can be a lot faster. And they're not exactly as accurate, but they're still pretty good. And these more advanced techniques are kind of out of scope for this class, but good implementations exist so that they can take care of all the details for you, and you don't have to worry about those things necessarily. Okay, I'm going to zoom through the last two slides, and again, we can take questions afterwards. So I think we've already sort of touched on this point, right, about it's actually kind of easy to imagine how the wrong distance metric may ruin your nearest neighbor, right? So for example, is Euclidean distance a good choice for digit recognition? Okay, if I give you a 28 by 28 grayscale image of a digit, is Euclidean distance a good choice in that native like 784 dimensional space? As it turns out, maybe not, right? Because we can sort of imagine digits that are pretty close to each other in Euclidean space, like this 9 and this 4. They have like very similar like thickness and things like that, but semantically they're very different, right? But they are closer, according to this Euclidean metric, than this 9 and this other 9, which is a lot thinner and kind of rotated and all these other kinds of things, right? And so this is a very easy way to define kind of the wrong distance metric, right? So if we wanted to define the right one, we have to be a lot more careful. And in general, if we wanted to do this rigorously, what we would need to do is think about the problem that we have at hand. So we can benefit a lot from, for example, computing statistics of the training data. That's kind of like the Mahalo distance that we were talking about earlier, or just having domain expertise with a specific problem. Like, for example, for digit recognition, we can think about the different ways that we can sort of think about transforming these digits, and then define a distance in that much lower dimensional transformation space. It's kind of the high-level idea, right? So here's, just a picture that I'll leave you with, where we can take a digit and then imagine different transformations. That's the second column here of like making it fatter, or like rotating it, or doing these different types of things. And then if we apply these different transformations, we start to get things that might be very far away in Euclidean space, right? But correspond to something that are close according to this distance metric that we can define. And so that's how we might imagine taking nearest neighbor and then applying it to more complex problems. Okay, we will stop there. Thank you, and we'll take office hours now.